we're finally ready to search for the elusive cubic formula. And the first step is what we call reduction to depressed cubic. What does that mean? Here we go. This is a depressed cubic function. So if t is our independent variable, then if it takes the form at cubed plus ct plus d, then it's depressed. And what you notice is that there's no t squared term. That's all it means for a cubic function. And generally for polynomials, if we have a polynomial a of x, that's the general form of a polynomial. If a of x has a n minus 1, this coefficient here, equal to 0, we'll call it depressed. So, what that's basically saying is that we don't have an x to the n minus 1 term at all. And the great thing about depressed functions, why we care about them at all, is because by making a linear substitution, more specifically by graphically translating it horizontally to the left and to the right, we can make it depressed. So over here we took ax cubed plus bx squared plus cx plus d, we shifted it over and we got a depressed version. So the equation here of the function is actually depressed. The great thing is, when you have a depressed function, if you can find a formula to solve that, you can actually solve all of them, because all polynomials can be made so that they're depressed using some sort of translation, some sort of substitution. Now let's look at the specific case. I went over a little bit of it right before. If we have ax cubed plus bx squared plus cx plus d, and we substitute x is equal to t minus b over 3a, we're going to get at cubed plus bt plus c. Now what does this mean? We have a lot of technology today, which means you can get a nice intuition for this without needing to learn any calculus or looking at this and just accepting it. We want to gain a little bit of an intuition. Sure, you can learn, make this substitution, it'll work. That's not very fun, and it's kind of confusing. It's like learning the quadratic formula without having any idea how we got there. So, let's say this is our cubic. You notice cubics usually have this odd shape, a bit of rotational symmetry always, regardless of the original equation, if you're talking about real coefficients, of course. If we translate it over, we get here. And I'm going to tell you, the fact is, this is the depressed version. If we look over here, what's one defining trait? Maybe you'll look at your graphing calculator, look at a few cubic functions. We actually have this point right here. We call it a point of inflection. It's not too important what that means, but it also acts as a point of rotational symmetry. If I rotate the graph 180 degrees, or pi radians if you're into that, what you'll notice is that it looks exactly the same. So maybe if you want, turn your head upside down, look at it, get a little dizzy, it looks exactly the same if you turn your head. And if we move it over a little bit, we end up here. This also has a rotational symmetry. We've just translated it over to the right a few units in this case. Turn your head, looks the same. And we're going to use a property of odd functions right now. So what if I just had at cubed plus bt, and let's say c is 0, let's pretend there's no c. This is actually an odd function, so it's going to have rotational symmetry about the origin. That's what this shape is, isn't it? If this point here, this point of rotational symmetry, was at the origin. Now you can think of the plus c as just bringing it up. So I hope you can see how this makes a little bit of sense with regards to what we know about odd functions. This is like an odd function, translated up, which is why we have the rotational symmetry. That's all there is to it, actually. But now let's look at how this is useful for us when we're solving cubic equations. Over here, we have at cubed plus bt plus c equals 0. So if we were able to make this substitution, we're solving for the roots, right? We set it equal to 0. We make this substitution, we're still solving for the roots. We'll set that this new function equal to 0, this new function in terms of t. Then we're going to divide by the leading coefficient. And here's the truth. When we divide by the leading coefficient, the roots remain the same, don't they? If I had x squared minus 1, we know the roots are plus minus 1. Multiply by 3 or divide by 3, and the roots are still the same. we'll look here again, and this is actually the form we need to look at now. All cubic functions can be put into this form by using a combination of this horizontal translation left to right, and then a vertical stretch, or compression if you want to think about it that way. So we go from ax cubed plus bx squared plus cx plus d always to t cubed plus pt plus q. And if we can solve all equations of this form, we can actually always find the roots of cubic functions. And that's what we're looking for, isn't it? That's why we like to do this little method here where we're reducing to a depressed cubic. If we do this, we only need to know how to solve this cubic equation in order to solve all cubic equations. Alright, let's look at a specific case where we're trying to depress a cubic function. Here we have 2x cubed plus 6x squared minus x plus 1. We know that's cubic, and we're going to make this substitution. X is equal to t minus b over 3a in order to make it depressed. Let's try it out. First, I'm going to say we know a is equal to 2, and then b is equal to 6, c is equal to negative 1, and finally d is equal to positive 1. Just so we know our coefficients. And of course, now we can definitely make the substitution. So x is equal to t minus, and we're going to plug in b and a. So it's equal to t minus b over 3a. What is b? Remember, b is just 6. And over here we have a. I'm off the screen now, but a is equal to 2. So we'll write that down. 2. We simplify it, and it turns out it's actually very nice. X is equal to t minus 6 over 3 times 2, which is t minus 1. We need to plug this in now, and we need to simplify. So, here we go. Alright, we're back. It wasn't a lot of fun, quite a lot of algebra. If you mess up your signs at all, you actually have the wrong answer. And that's why I don't think this is very fun, but it is going to allow you to show off to your friends, because now you can solve cubic equations. Well, at least you can do this first part where you're turning it into a depressed cubic function. So, we start 2x cubed plus 6x squared minus x plus 1. We know a is 2, b is 6, and we need to make the substitution. X is equal to t minus b over 3a, and in this case it's just t minus 1. Most of the time you're not actually going to get very nice numbers like this. I picked this problem because I knew the substitution would be nice. In reality, it might not be like this, unfortunately. We plug it in, we expand it, now we group the like terms, and here we have it. We have 2t cubed plus 0t squared minus 7t plus 6. And remember, if we have 0t squared, it's like we have no t squared term, and it is indeed depressed. So we could also say it's just 2t cubed minus 7t plus 6. And there we go. This was a nice example of how we can reduce any cubic function to a depressed cubic function of this form.